Okay, hello everyone. This is a continuation of the making a synthesizer thing I'm doing-ish project, whatever that is. And today's going to be a little bit bigger because we're going to be talking about timing our MCU to be fast enough, and a little bit of code organization is going to be implemented to keep the overhead every output cycle for the DAC. Keep that overhead low, and we're also going to talk about connecting things up to MIDI. Let me also talk about the last videos. So I've made quite a number of mistakes in the other videos and what I've said that I immediately after I said it I knew were not true. For example, when I was talking about the resolution on the DAC, that absolutely has nothing to do with how high of a frequency you can output. That has everything to do with your output rate at which you update the DAC. Its resolution has nothing to do with how high in the frequency spectrum you can get to. So we're going to be talking about doing MIDI today. What the music industry came up with is running UART through a cable that doesn't actually terminate into anything electrically. It just goes into this little chip right here, which is an optocoupler. So it just flashes a little LED whenever there's current, and then you have like a little solar panel that reads the flashes of light, and then that gets amplified and turned into electricity, and that ends up being what you read. You don't have to worry about connecting two different pieces of equipment with their own power supplies. If you do that, their ground potentials could be at different levels, and then plugging in those cables could end up resulting in you shorting out your system. We'll start off with, though, before we get to the MIDI stuff, we have to redo our timing with the microcontroller. And I'm going to redo this a little bit. We're going to increase this clock speed from our 3 megahertz default, and we're going to max it out at 48 megahertz. The first thing we need to do is we're going to initialize the device with this, with a number of settings here for the clock. So go ahead and I'm going to just separate that out. So all right, we're going to move this watchdog stuff into here. Let's go ahead and move this in here. All right, so this code will have a mix between some, do things in a bitwise fashion and using driver lib files. Some things seemed easier to do with driver lib, some things just are unnecessary. So this is a bit of a Frankenstein code that I'm going to write here. Anyways, to increase the speed for the clock, we're going to have to increase or go to a different voltage mode for it. So this one we can just do quickly with the driver lib library. So set power, state, we're going to change it to PCM, AM, LDO, vCore 1. So you have to do this if you're going to go above 24 megahertz. All right, another thing to notice when you get this speed is that you can't write and read from flash at that speed. It's just not fast enough, especially writing. Sometimes with flash it'll take a couple write attempts before you can verify that it's correct, or it just won't write. So what we're going to do is we're actually going to subdivide the clock that's going to the flash memory. So if you try and read and write, it's actually writing at a division of the clock speed that you're running at. So here you do flash control, set, state, flash bank 0. There are 2 banks. And we will go ahead and do that to the other one as well. And I think that's good. Also, what we also want to do besides prepare our code to handle faster processing speeds is we're actually going to enable the floating point unit as well. So if you enable module, this is also very easy to do. You just call this from driver lib. Now we can actually get to setting the frequency for the clock. Let me just comment this really quick. So this is right, and this one width. And floating point unit we're actually going to use later on. I'm just going to add it in here so we don't have to touch this again. The floating point unit we're going to use so that way we can utilize the sine and cosine functions and things like that to make some of the waves, essentially. Besides that, oh, and some frequency calculations as well. But we're not really going to use it after that, because since we're going for speed here, everything's going to be done with fixed point integers. So okay, now we can set the clock speed. So we're gonna so first thing, the clock in here does not run off a crystal, obviously, if we can set it. It uses what's known as a actually I just forgot what the D stands for. Well, anyways, I forgot what the D stands for. It's called a DCO. And basically it's a capacitor based clock where you apply a certain voltage. The capacitor takes a certain amount of time to charge. When it hits a certain level, then it opens up a circuit that basically grounds it and allows it to drain out. And that period of charging and then shorting out, or maybe not shorting out, but just letting the capacitor drain, that up and down fashion of the voltage is what you're looking at to set your clock. What we're going to do is we're going to change our submaster clock and another clock as well. And we're going to set those at a lower speed so that way we can deal with some of our peripherals much more easily and more appropriately. So we're going to set the master clock, the high speed clock source, and then submaster clock. So here, it's somewhat the same command for all of these. So first thing we're going to do is we're going to set the master clock to the DCO. The master clock is what controls the code speed. So CS MCLK. So we're going to set the master clock. We're going to connect it with the DCO clock, and the DCO is running at 48 megahertz. And we're just going to give it a 1-to-1 ratio. So now that that's specified, we have the master clock running at the same speed of the DCO. The next thing we're going to set is this high speed clock. We're also going to tie it to the DCO, but we're going to divide it by 8. And the last thing is the submaster clock. Also tied to the DCO, this one's going to be divided by 4. So all in all, the master clock is running at 48 megahertz. The HSMLK is running at 6 megahertz. And then our submaster clock is running at 12. Alright, so I think that should be it for the clocks and the initialization of everything. Let's go ahead and build it, make sure everything builds fine. And it didn't. Luckily, it's just a spelling error. Alright, cool. So this is fine. We're using the driver lib, the driver library here. We didn't get any errors from that, so importing that went okay. Alright, cool. So we have the clock running just as fast as we want, or all the clocks. The other thing that we're going to do is we're going to set up the UART. UART communicates using UART. The MIDI standard uses the UART protocol. So we're just going to use the normal UART interface on the MSP. In this case, what we'll need to do is configure a UART structure that has set parameters. So this is going to be the UART configuration structure. So, for the MIDI interface, MIDI is, like I said, just normal UART. It runs at a baud rate of 31,250 bits per second. And it's also least significant bit first, and without parity. So let's go ahead and make this. Set this as a constant. Yep. We'll just go ahead and do this. All right. The first thing that gets specified here is the clock source that it's tied to. So our clock source that we're using is going to be the submaster clock. Submaster clock is running at 12 megahertz, just in case you forgot. The next thing that goes into the structure that's looked for is something called the BRDIV. Let me also go and show you, I guess, the layout of this. So let me move over here to a screen capture. So this is the UART interface for the MSP432. It's actually the exact same peripheral design as the MSP430. Is it the exact same? The layout with the clock structure is exactly the same. So if you're used to the MSP430, you know how to calculate bit rates for that. You're fine. It's just the same thing. But just a quick look here. This is the receive input pin. Goes into this buffer. Right. This buffer is run by a clock source. This clock source, you can choose to tie it to UCLK, which is an external clock. ACLK, which I forgot what that is actually. Or you can tie it to the submaster clock. And then the BR clock is actually just the clock for the UART. Now, you can set a prescaler on it. And one thing to note is if you do use oversampling, so if you have the clock speed overhead to do that, then you can just do that. What it does is it speeds up the signal reading by 16 times. And so then it can sample and make adjustments within those 16 additional readings of each bit that it tries to take. So let's go back here and set the BRDIV. Basically, let's go here. We're running our clock source at 12 megahertz, and we're using a baud rate of 31250. That's what the MIDI interface calls for, which gives us a number 384. We will be using oversampling. So oversampling takes 16 measurements per bit that it thinks is there. So in order to account for that, you can divide that by 16, and then 24 becomes the remaining factor that you have to decrease the speed by. This is actually the BRDIV, so the clock divider that's going into the source. It's not a decimal point, which I'll get to in a little bit. But let's go back here. So 24, this BRDIV. So we divided the clock source here by 24. We have no decimal points, so we have a couple different modifiers. We're just going to set those to 0. So this is the, it's labeled as the UC BRF, F meaning the first modifier. The first modifier register. And then this next one is the BRS. And this is the second. That's it. And so but they all look very similar. C#, C++, or C. So then also the MIDI specifications. The UART communication protocol does not use parity in this case. So according to driver lib, you write EUSCI A is the which one we're using. UART, no parity. All right, we're also going to specify that it's the least significant bit first. We're also going to keep it in UART mode. You can do a couple other things, but we're just going to be using basic UART. It's just going to be used for fun, man. Basically, I have a piano that I don't really know how to play that well, but I want to make some dope beats. And if it sounds like a piano, then I feel like I should be playing much more advanced, and I'm not. So I'm just going to make a cool synth, man, and get some really, really awesome sounds going and just, I don't know, screw around with it. Maybe make some better music for this channel. I don't know. Doesn't matter why I'm making it, really. And then there's one more thing we have to specify. Up until this point, we haven't specified that we're doing oversampling, so let's go ahead and add that in. And actually, that's it. All right, so at this point, we've specified our parameters to set up UART. Let's go ahead and actually set up UART itself. So what we're going to do is we're going to go up here. Actually, I'm going to move this. We're going to do another initialize UART. All right, so we're going to initialize the MIDI stuff. There are a couple things we have to do. One is to make sure that we load in. Let me throw it under here. All right, so after we get the clock speeds and stuff, we're going to initialize the MIDI. What it's going to do, first of all, is it's going to allow the pins on our microcontroller to actually be configured in UART mode, because these pins have a couple different peripherals attached to them. They can be just GPIO pins. Some have additional secondary functions and third functions, tertiary functions. I forgot the name of it, but they have additional functions that you can do. Sometimes only 2, sometimes 3, sometimes more. In this case, this microcontroller defaults to GPIO to begin with, so we need to make sure that the UART pins that we're using don't stay in GPIO mode, but actually connect up with the UART peripheral itself. So to do that, we're going to, actually, let me show you where it is. There we go. Let's move over. So the MSP 432 board here, you can see that on pin 3, we have this UCA2RX and UCA2TX. This is one of the 2 UART channels on here. 2? I won't say 2. It's just one of the UART channels on here. There's more than one. One of them is used for programming, of course. But this is on pin 3.2 and pin 3.3. So to do that, we say P3 cell 0. So there's like 2 select pins, so there's like 4 different options. If they're 0, if P cell 1 and P cell 0 are both 0, then it just is GPIO, sorry. In this case, we want to make P3 cell 0 be 1. And so we just set the second pin of it to 1. So what this did is set point 2. So this is actually pin 3.2 equal to 1. And then we're going to set the select 1 to actually 0. Alright, so pin 3.2 is set up as the receive buffer, or connected to the receive buffer of UART. We're going to do the same, just so that way all these are connected. So this is actually 0.3. So pin 3.3 is now the transmission buffer. So when the code runs through this and changes these register values, the select register values, these pins will now be tied to the UART peripheral. We also want to load up all the settings that we just made for the UART peripheral, so that way it's at the correct baud rate and all that crap. So I'm going to type this in here. Yep. And this is going to have this structure. All right. All right, cool. So we have all that loaded. Now we're going to enable it. CI. Yep. Module 2 is what's connected to pins 3.2 and 3.3, if you're wondering what A2 references. And now we're actually going to be using an interrupt because we don't want to pull. We just want it to, if it sees a MIDI signal, don't chance missing it. Just take it all in, and we're going to save it to a FIFO buffer. So for this, we're going to map UART, enable, interrupt. There we go. Interrupt has 2 R's, right? Yeah. All right, and then we're gonna, so this enables the interrupt for in UART to be able to trigger them. Then we're gonna actually do it for the MPU itself. Uh, um, 7. There's 7 of them. All right, cool. So we've set up these GPIO pins to actually be connected instead to the UART interface. We've loaded our configuration. We've enabled the module. Then we've also enabled its ability to do an interrupt and then for us to receive the interrupt. So that's that for initializing the MIDI interface. And now we can actually build the interrupt itself. Here we go. Okay, so we're going to throw the interrupt here at the bottom. How do I want to separate this? I'll just separate with a bunch of these. 80 of them. That's classic. All right, so this is the UART interrupt routine. If we receive an interrupt, then we need to check it to see if it's the receive interrupt. Otherwise, we don't care what it is. So if the interrupt flag for our thing is high, and this is a bitwise and FG. So if it's the interrupt flag of the receive interrupt flag, so this, if I remember, is actually we can check it now. This should be, oh wait, I can't do that. It's going to error on me. I need to clean up some things I misspelled. Okay, so what this is like an interrupt flag vector. If the one corresponding to the interrupt flag you're interested in, if that bit is 1, then it'll be flipped here. Or if the one of your interrupts is triggered, then one of the bits here associated with it becomes 1. This is a name that's just like a bunch of zeros, and then it's got a 1 bit corresponding to the receive interrupt flag. So if you bitwise and this, if the interrupt that was triggered matches whatever this one is, which is for us the receive buffer, if they match, then we're going to go into this loop, basically what we're doing. All right, cool. So now that we verified it's the right interrupt that got triggered, what we're going to do is clear it. So we're just going to take wherever that 1 was, and we're going to make it 0. Just like that. All right, now we're going to mess with a FIFO buffer. The interrupt routines, you can define variables within them, but the only external variables you can access, because you're not passing anything into it, and you're not calling it. The interrupt handler is actually calling it. The only other variables it can read are global variables. So our FIFO buffer is going to be a global variable, and we're just going to call it MIDI buffer. MIDI buffer sounds good. So, and also because this thing can be read through an interrupt routine, it's not only read through code that the compiler is going to recognize exists. It could change without the compiler knowing or the processor knowing, because it's changed through an interrupt. Or information is added to the buffer through an interrupt. So to signal to the compiler that we don't want to optimize this out because it's going to think we're not going to be updating anything in it. We're going to mark it as volatile. And we're just going to make it ints. Everything's going to be integers pretty much. And we can go ahead and make it 32 bytes large, just for fun. What we're also going to go ahead and do is create a couple counters or indices that we're going to use to follow this, use with this FIFO buffer to follow the information. One is going to be a write count. And a read count. So these are indices for which one we're currently reading and which one we're currently writing. So let's go back here and actually enter information into our buffer. Here we have the MIDI buffer and the current index that we're writing to. And it's actually going to be the receive buffer. So, yeah. Right after we write something into this, we need to update our counter or our index. So this is going to be incremented by 1. And this buffer is a 32-bit buffer. 32-byte buffer. Byte? Yeah, 32-byte buffer. So we're going to allow it when we hit the position 31, it's just going to roll over back to 0. So we're going to bitwise AND this with 1F. And so there we go. Doesn't matter where the write begins at, as long as it's between 0 and 31, and which we'll specify later. But anyways, we're going to write in whatever the current position is, what we've received, and we're only going to get to this part when the interrupt triggers, which means something's been received. And then as soon as we receive it, we're just going to increment our writing index into the buffer by 1. The only thing now is to actually get the information from the buffer and interpret what it is. So let's go ahead and make a declaration of this. Actually, I'll separate it. So we're just going to call this get MIDI changes. So whenever this is called, it's just going to check to see what's in the buffer and figure out what it is. And once we get the complete MIDI message, then we'll have information that we can use. So let's throw this here. So MIDI FIFO buffer. Okay. All right, so in order to do this, we're going to need to know what the MIDI protocol is. So let's move back over here. Okay, so the MIDI specification calls for certain types of messages. And there are two types of messages. There's these things called status bits that begin with a 1. And so, or status bytes, where the most significant bit is a 1. If it begins with a 1, it's telling you that something's happening. So in this case, if it's 1 and ends and is followed by 3 zeros, it's a no off event. MIDI protocol is just for music, so specifically this is note off. If it's followed by 001, then it's specifically a no on event. So that's a key press or a key depress. In case of the no on event, if you see this, you know that there's going to be 2 data bytes that follow it. So the data byte begins in 0. If this began with a 1, it would think it's another status byte. So another like, hey, we're going to update something else. So if this started with a 1 and it saw it, it would abandon whatever it's doing, whatever's reading these MIDI messages, and just start over. So otherwise, it's going to give us data about what's going on. So for the no on event, we receive, okay, this is a no on. So a key's been pressed. It's from this channel or this instrument or whatever. Or if it's a really big instrument with multiple channels, then you'd have to set that up in software or whatever. And then it's followed by 2 data bytes. The first byte with all these Ks tells you what note is actually pressed. The next one is a velocity, and this is a loudness. And this is only 7 bits, so it's 0 to 127, whatever that is. And so that's your range. If you, just for a caution, if you're dealing with multiple keyboards, some keyboard manufacturers don't follow exactly the MIDI specification. So for a note off, instead of just doing a note off event, they'll do a note on with velocity 0. So you have to work that into your code if you're going to build a synthesizer. Anyways, for us, we're only going to care about note on and note off so far. We could add other stuff like pedals and things, but we're not going to mess with that now. So in order to understand these MIDI messages, we're going to read the FIFO buffer, check to see if what we're currently reading starts with a 1. If it starts with a 1, we're going to abandon whatever we're doing and see what it is. If it's followed by 001, then we know it's a note on, and then we're going to wait for the next data bit. The next data bit should tell us what the note is, and if we receive that, then we wait for the next data bit. So if the next data bit is all zeros, we interpret that as an off. If it's got a number in it or exceeds the threshold, we're just going to say it's on. I've got kind of a hack way of doing this through a series of what I'm calling are like locks. It's just a bunch of if statements and then waits for the next moment. So in get MIDI changes, how we're going to read it is first we're going to read if there's something in the FIFO buffer, because at this point, anytime we receive something from a MIDI instrument, it's going to be thrown into the FIFO buffer. So the first thing to check is to see if we have new information waiting for us or not. So to do that, we're going to start with just naming it. If there is MIDI info we haven't read yet. All right, so if, and this is where the count comes in. We haven't messed with the read count value, but we have messed with the write count value. Write count value is just some value. So if the read count is not the same as the write count, then there's information between those two indices, and we want to read it so we can catch up. And so we're just going to follow it. So if for some reason we all of a sudden read in like 20 MIDI messages, then we'll be able to make up all those steps until we catch up. And of course, you're assuming that you're reading fast enough to catch up and you're not going to overwrite things that you're trying to read or that you're trying to read next. All right, so now we're going to recognize, okay, we have information waiting for us. So we need to read the MIDI byte. I don't know, that hasn't been read yet. So to do that, we're going to say, we're going to specify MIDI byte. There's just some variable that we're making up, and it's going to be the next thing in the MIDI buffer that we haven't read. So, let me increment this. And this is basically following the same thing that we did before in the interrupt. Okay, so at this point, if these aren't the same, then what we're going to do is read from the MIDI buffer, and after we read from it, we're going to increase the count and also allow it to roll over the same amount as the MIDI buffer size. And this is the same thing as what we did here in the interrupt. If we receive something, we're going to save it in a certain location and then increment forward. So they're going to chase each other. And also, just note that if you're going to do this, you have to do just a not equal to, not a less than sign, just because you're allowing rollovers in this case. And who wants to keep count of rollovers? You would just increase your buffer size. So at this point, we've caught up with information that we still have yet to read. And so now we need to interpret what it is. Sorry. So if the MIDI byte is a command, so if it begins with 1 is what I mean. So if MIDI byte, and it's 8 bits, so this is how I'm going to do it. I'm just going to right shift it by 7, and if it's 0, then that first bit was a 0. If it's 1, then it'll be a value of 1. We'll pass through this, or we'll enter into this. Okay, so if it's a MIDI byte, what we're going to do is we're going to set a flag. This is a flag that says we're currently waiting for data bits or not. So, which I'm just going to say whether it's important or not. So this is this flag is actually a counter. If you saw before this, or if you remember me saying that if you receive, like, say, a note on, you're waiting for 2 data bytes after it. But some things, like for example a program change, only waits for 1 data byte. So you have to be aware of counting how many bytes you've received that are data and so forth. And if you've received everything that you need, or if you need to halt halfway through. So this important flag is what's going to help us keep track of that. So 0 means we're currently looking at control messages. If it's a 1, we're currently looking at the first data byte. If it's a 2, we're looking at the second data byte. Is basically what I'm going to be doing with it. So we've read our first MIDI message. If it's a control, we're going to see, we're going to say, hey, it's important. So we're going to reset the important flag. And now we're going to check to see if it's relevant to us. And by relevant, I mean if it's a no on or no off command. So if a key's been pressed is what I'm concerned about. So if note, if, yeah, has been pressed or depressed. So if, I'm going to do it this way, 0x F0. So this is a bitwise and. This just makes it so that way we're only looking at the 4 most significant bits. So if that is the same as this, and this 9 is a no on command. Yeah. So this is an 8. This is a 9. So for note on and note off. So if our MIDI byte is a note on or a note off, all right, then we want to pay attention because a key's been pressed or let go. So first thing we're going to do is say, hey, this is in fact important. Both of these require 2 data bits. So we're going to be looking at the first one. And we're going to just take note of what the MIDI command was. All right, so this is the first part. We've just recognized that we are receiving a no on command from our buffer, and we need to see what that data is. So yeah, in here. So now we're going to wait or read what it is. So one thing to note is that if what we just read was the command, it's possible we could have already caught up with the write counter, which means there's no more information to read. So we can't immediately read what the data bytes are, because those could either still be coming in or haven't actually been sent by the device yet. So we're going to match this up with an else if, and that way we read it on the next go round. What this also does, and this relates to optimization, is that you don't read too much code per call of the get MIDI change. So every time you read this, or every time you call this function, in this case, you check if 2 values are equal, you assign something, increment it, and then change 3 values and do a couple checks, and that's it. And later on, you do about the same amount of work. You don't do this and then another set of instructions at the same time. What this allows you to do by doing else if statements is let's say you're trying to run this thing as fast as possible. Well, when you press a note on command, then you get 3 bytes to read. Instead of checking and interpreting all 3 bytes all at once, you break it up between cycles in the synthesizer. That way you're only doing a little bit each time, and that gives you more computation room to do the actual synthesizer part where you're synthesizing the sound and outputting it to the digital to analog converter than you otherwise would have. Because if you read too much information, you mess up the timing, then your sound wave that you're outputting is going to be screwed up. There's going to be a pause in it or something like that. And that's actually very, very audible. And so we want to do as little per cycle as possible. And if we're running this thing at 40 kilohertz, then basically if we have 3 MIDI commands, we break it up on 3 cycles, then I mean, you're still running way above like, 10 kilohertz, which is fast enough to think it's real time. When you press a key and then hear it, that delay is so small, you're not going to notice it. So that's why we're going to break it up like this, both to handle the FIFO buffer. Instead of saying, hey, we're going to wait for 2 more, we're just going to process it in steps. So if it's important, so we received a note on, note off, so the thing's important, and want the note value pressed. So if the important flag is 1, so if this is a note value, then we do I'm subtracting 20 here on the next value, because actually the first note on a piano for A0 begins at number 21 on the MIDI spectrum. It allows you to get lower notes for an extended keyboard and stuff like that. So we have that. So now we have the note that was pressed. So we're going to increment the important flag. So now it equals 2. So at this point, we've got this information, and we're looking for the velocity level. So else if you're also if you've noticed things like MIDI CMD and some other variables have not been declared yet. I'm going to do that. These are going to be global actually, just to make handling it easier. So we're waiting on the velocity value. Okay, so we're waiting on the velocity value. So if it's actually a note on command, and so this gets into what I was saying. Some manufacturers will send a note on command with a velocity 0 to instead mean a note off instead of sending a note off command. And you need to take that into account if you're going to be keeping track of on and offs. Otherwise, you're going to think a note got pressed twice if you press and release it with some keyboards. So if it's actually a note on, so if MIDI byte is greater than 0, And okay, so if the velocity isn't 0 and it's actually a note on, then we're going to say, hey, a note's been triggered. And I'm not going to worry about velocity at this point. Because I'm building a synthesizer, I'm actually not going to do input sensitivity into it. I'm just going to say everything's at the same volume, and I'm going to allow the amplitude to be completely controlled by the synthesizer itself and all the dynamics of the sound and so forth. We can tweak that and add velocity control in there, but for now we're just going to keep it simple. This will make all these things are little now, but when you get to writing code, then you have to keep track of the rest of what's going on in the synthesizer. And if I add volume now, it's going to change a couple things. And I'm trying to keep some stuff slimmer. That's a little unnecessary, but we can always add that in later. Okay, so if it's a true not on command, otherwise it's not. Just simple as that. Then it's a note released. And yeah, so now we've read that we got a note on or off. We've read which note, and we've read the velocity value. So now we can say the important flag equals 0. So now we're always going to be avoiding these two if statements and only checking to see if something else is a command. The reason why you want to do that is what I said earlier about maybe you've missed one of your MIDI messages. Well, if you miss a MIDI command and you just end up receiving a data, then it's immediately going to go into here if you don't reset this and discriminate against these two statements. So, yeah. Oh, no. Actually, let me move this a little bit. Actually, I'm going to change something. So, if, because I just forgot what does happen. So, there are some cases in which, scratch what I just said. There are some cases where after you receive the note on or off, and then the note and the velocity command, in order to speed up communication, some manufacturers do just completely omit sending the next command byte that says note on or note off. Instead, they just send the 2 data bytes for note velocity, and that way if you push a key repeatedly, you just get note velocity, note velocity, note velocity, and it allows you to more rapidly change note values. So if you do really fast finger movement on a piano or something, or you're having a computer send a bunch of MIDI commands through, then if you're just playing notes, you can play notes a lot faster. Otherwise, you're running a third of the time slower because you're having to deal with, instead of 2 commands for a note, 3 commands, or 3 bytes, and interpreting it. So actually, after we get the velocity command, if it's, let's see, how do I have this set up? Yeah, okay. So after this, then no matter what, we've received note press or release. So we've gotten the velocity command. So we got velocity. Now we want a note. Next, note, val, and velocity. And this is only if This is only if, not a command. Yeah, so after we get the velocity, we're going to immediately go into this if statement that checks to see what the next value is. And we can do that because if the next one is actually going to be a command, then it'll actually automatically trip this if statement, go in here and reset things. So actually we're okay. If we, for some reason, something messes up and our important flag, for some reason, don't meet this criteria, our important flag is neither 1 nor 2, then what we're going to say is just set it to 0 and wait for the next. So if all else fails, just wait for the next command. And that's how we're going to play the game. I believe that's everything we need for getting MIDI changes. So at this point, when we play keys on the keyboard or whatever MIDI controller that we're using, it's going to fill up a FIFO buffer, and we're going to chase the values in it and get MIDI commands. We're going to read it. If we get a note on or off, we're going to get the note value, and it's going to be saved to MIDI note value. If it's a note on, we're not going to worry about velocity. We're just going to see if this MIDI note value is either a on trigger or a release. That's it. So this note got turned on. This note got released. That's it. And we're going to call this every step of the sound generation process. So as soon as you press a note, we can update the sound generation to match what note has been pressed. So, yep, that's what we're going to do. All right, so I've written all this code. Let's see if it builds. If I miss something, I apparently missed something. Oh yeah, I never specified these things, so I'm going to make these global variables. So let's find a place to put that. So this is going to be variables for the actually, I need to label these too. Okay, yeah, these are all variables. So this is going to be for MIDI interface and FIFO buffer. Cool. We also have some for MIDI counting and value storage. This is where we're going to do the MIDI command and stuff. So UART underscore T. So this is a MIDI command that was called. We don't care what it is. It's going to be written as soon as we need it. Here's the important flag. Same thing. That's always going to be written. MIDI note value. Then we have notes that are in play or out of play. So the MIDI input. So this is going to be where the trigger, release, and volume and all that is. So we don't want it to say anything's there yet. We're not going to be using note volume, but I'm just going to throw it in there in case we add it in later and I don't forget. Yeah, I already wrote it. Let's just leave it. Okay. So Let's see if that builds. Important flag. Yeah, okay, we're okay. So there's one more thing that we have to do in order to test this out, because now we can read stuff in, but how do we get the response that something's going on? Well, what we can do is flash a light every time we see something. So let's go here in main. We have our forever while loop here. And I'll just make sure I'm not going to do anything reckless here. Okay, so what I'm going to do, I'm taking pauses because I'm referencing code that I know already works, so I don't lead you guys too wrong. So that's what those pauses are for. So what I'm going to do now is create something called, or a routine called, well, routine, some function. Something that we're going to call that's going to be the sound path. So the sound path is the path that you take to figure out what the sound is and generate it. So let's go ahead and make this. Put it up here. All right. So the sound path is going to be kind of the overall flowchart of what's going on. So yeah, let's start here. The first thing we want to do is check the current note. If anything has changed. The reason why if anything has changed is here is going to be our get MIDI changes thing that's going to read our buffer and check to see what we're going to do. If there's no new information, nothing happens. So I was just going to skip this. So we're going to see what note is pressed or has gotten pressed or not. And we're also going to make something called a note sustain. So I'm going to go off the beaten path. So sorry if there's a little bit of mistake that appears. I'm going to make this note sustained. This vector with 88 notes, that's just how many I got. And a keyboard, we're also going to go here. And let's see. Okay, if the note's actually a note on, we're going to go here. We're going to check to see the note. So MIDI note val is actually going to be our index equals 1. And then if it's been released, so if it's not a true note, we're going to set it back to 0. So if we have a real note on command. That is, we have a note, velocity is not 0. We're going to set our vector with 88 keys. Whichever note was pressed is going to become a 1. As soon as we let go, that'll become a 0. If we press multiple keys, then there will be multiple 1s. So just make sure, or to see if anything's going on, what we're going to do. Oh man, you got a mistake? What? So we're going to get MIDI changes. If we, what did I just name it? Notes sustained. So if notes sustained ooh, I'm going to do something really tricky here. By tricky, I mean if you don't change this afterwards and just not do this, you'll end up with mistakes later on. So I'm going to do something slightly different. What I want to do is we're going to get the MIDI changes. If a note's been pressed, we want to turn on a light. So if note sustained is greater than 0, or just is not. Yeah, okay. Yeah, that's fine. If note sustain is not a bunch of zeros, so MSB 432 is a 32-bit register, so we have 32 values we can put in there. If it's greater than 0, then one of the notes is currently being pressed, and we want to turn on a light. So for this, we actually need to enable the lights. So we're going to make another, we're going to make another statement. Initialize the GPIO pins, because there's some onboard LEDs that are connected to GPIO pins. So we're just going to set one high for a light and turn it off for no light, and that's going to be our check to see if we're pressing notes or not. So let's add that here. Whoops. I did initialize MIDI, which I meant to do UART. Sorry. All right, so init GPIO. We'll come down here. Okay, so these GPIO pins, remember for the UART, we had these select registers that we had to make sure that we set so that way those pins are directed to the UART peripheral. Instead, we want to make sure that they're in the GPIO peripheral. The default is usually set to GPIO anyways, but I mean, when you first turn it on, who knows what's in those registers if you don't explicitly do it. So what we're going to do is make sure they're 0. So we do have one red LED that's connected to the first port of the GPIO pins. And so that's going to be P1 SEL0 for the first select. We're going to set that to be, well, 0, or the first pin of it to be 0. Just like that. We'll do it for the second select as well, or the 0 in the first. The next thing is going to be the direction. So dir if it's, let me just make sure really quick. I want to say 0 is in and 1 is out. Oh yeah. So we're going to set the direction to the direction bit for that pen to be out, so that way we can send out voltages. And the P1 out, we're going to set to 0. That means it's just tied to ground. If we set to 1, it's going to be tied to 3.3 volts and turn it on. So all right, cool. So that's now enabled. So if any note is sustained, we're going to turn on this output. Like that. Otherwise, it bothers me. Otherwise, we're going to turn off. Just like that. So everything should be set. At this point, let's build it, make sure. Note. Oh, it's notes. Sorry. All right, so just quickly before I connect everything together and show you the light blink when I push a key on my keyboard, we're going to initialize the device with a really fast clock rate. It's going to be set to 48 megahertz, really fast for this board. Then we're going to set up the couple of the GPIO pins to their UART peripheral, and that way we can communicate with the UART information going through the MIDI ports. Then we're going to set up a pin to toggle a light, and then we're going to sit in this sound path thing. In the sound path, while it runs through this over and over and over, we're going to get any changes that exist, and then what we're going to do is check to see if any notes have been pressed. If they've been pressed, we turn on a light. Otherwise, we're going to turn off the light. And that's it. MIDI changes read information from a FIFO buffer that is going to be populated by an interrupt routine. And the interrupt routine just checks to see if there's a MIDI, if there's any information that's sitting in the read buffer of our UART connection, and it's just going to pop it in there. And yeah, and we don't sense a trigger or a release until all the information for that command, for a note press or release, has been processed. So if anything happens prematurely, then we're just gonna, ignore it. So, yeah, basically we're just gonna turn our keyboard into a big turn on a light with keys sort of thing. So let me switch things here. So here's the board we're going to be using. Here's that MIDI interface again. Ooh, fun view. Okay. Got the other end of our MIDI cable. Got that plugged in. Turned it on. All right, so there's a keyboard. Everything's connected. And basically, we're going to look to see if a LED here blinks. So I'm going to hit run. And let's see. Oh, it's not working. Oh, I missed one. That's it. I hope so. It may not have completely initialized and just didn't load everything. I forgot you do have to specify one stop bit. So it's possible the buffer was just open and never ending. So EUSCI A UART 1 stop bit. Ah, beautiful. I added it. That wouldn't make any sense. Okay, hopefully that was the issue. So here we go again. One more try. So run the code. And there we go. Check that out. So push a key down, light stays on, lift it, light goes off.